yeah, this is the title, so I will try to explain you how you can use logic to actually predict humans' behavior. And by logic, I mean sort of modern logic, so a lot of computations, a lot of semantics, a lot of interpretation. Yes, so of course, you may start by asking me, but why are you even going to talk about that? Isn't that the case that logic is a part of cognitive science? And actually the answer is unfortunately not really, and it has historical roots that I will very briefly recall here. So as we all know there's this divide between psychology and logic, between psychology and formal theories that actually goes back in time. And to cut the long story short, how you can imagine it that, well, logic started in antiquity, famously with Aristotle and then Stoics studying propositional calculus and quantifiers, all sum and so on. And then somehow in more modern times, mostly promoted by Kant, there was this view that logic laws are really the fabric of thought, so that everything, if you really talk about thinking needs to be logical. So everything which is sort of illogical, then it's not really thinking. And then there was a strong opposition against that in the 19th century, where people turned the page and said, like, look, actually it's the other way around. Actually, laws of logic are laws of thinking. So actually laws of logic are psychological laws. So what logic does, logic studies thinking. And again that, well, for that there was a strong opposition, mostly in Frege's writing, so-called anti-psychologists that sort of enforce separation between logic and psychology, because logic is somehow objective, right? So the reality that logic studies is somehow independent from what each of you think or is thinking right now. But notice that it all happened in this very exciting time of the end of 19th century and the beginning of 20th century, where actually two things happened. So on the one hand, this anti-psychologists somehow started mathematical logic, started modern logic with Frege, logic focused more on foundations of mathematics. But also this is exactly the time where modern psychology somehow took off the ground with Wundt, with the lab in Leipzig, like sort of first experimental laboratory in the history of psychology. But then there was this divide. So logic was more focused on foundations of mathematics and psychology was like experimental psychology. And somewhere in the 60s, there was this growth of cognitive science, right? So famously, people proposed that maybe we should look at cognition from a more interdisciplinary perspective, linking psychology, linguistics, philosophy, and also formal sciences, like mathematics, statistics, computer science. It was a relatively young discipline back then. But somehow you already see there are bits of logic in all those formal sciences. And it also happened more or less in the same time when there was this turn in logic, there was this turn in thinking about logic. So maybe even not about logic, but logics. So somehow there's no one particular logic. Logic is not something normative. There are many logics, and you can pick your favorite logic if you want to model that task, or pick a different logic if you want to model a different task. And also logic stopped being only like sort of syntactic, proof theoretic, but also started to be very much semantic, very much about interpretation, and also about computations and processing, right? So this sort of opened the door to the close collaboration. But unfortunately, and I can tell you from my own experience, if you go to a room and you sit with cognitive scientists and logicians, it's not so easy. So there's still a lot of this tension between logic and psychology. So you really need to work out to make it happen, to actually make the real collaboration happen. And I think that there is still not enough. So what I would try to advocate for, increasing collaboration. And this increase should happen by this modern view of logic, where logic is sort of focused on interpretation, information processing, and computations, semantic approach to logic. Yes, so I would claim that logic should be a part of CogSci toolbox, and at the current stage it's not. I mean, parts of it are sometimes, but it should be more. And of course, you can use logic for many purposes in cognitive science. So you can try building cognitive theories. So very often when you read psychological literature, you get these really nice theories, sort of stories about how different parts of cognition works. And you would very often would like to know more, so maybe you would like to formalize that, maybe you would like to make it more precise, make it mathematically more rigorous, and for that, of course, logicians and philosophers, they come handy. This is what we do. You can also use in computational modeling. So what these days cognitive scientists do a lot, they build models, right? So they build models to simulate our cognition, and then they see how those simulations work, and they compare them with sort of our processing in reality. And of course, when you think about these computational models, well, logic can give you some sort of algorithmic insight, for example, right? Or can try to clarify. Those models very often are quite messy. And another thing, which is maybe less obvious, is that you can actually use logic to help designing experiments. And then also, if you think about that, if you think about experiments, there's like two parts. So one thing is design, setup of the experiment, then you run an experiment, then you have to interpret data. And of course, both those parts, design and interpretation, they are very strongly linked, and it helps to make clear distinctions at that level and clear predictions. And again, this is the place where logic comes in, or logic should come in. So let me make one point I would like to make here. So I don't say, and I want to claim more, that logic is useful for the psychology of reasoning. So what you see mostly when you look at logic, logic applied to psychology of reasoning. But I want to make a stronger claim. I want to make a claim that logic is a general tool that can be used in investigating all sorts of cognitive processes. Perception, maybe vision, reasoning, social cognition, reasoning about beliefs, intentions, and knowledge of other people. Right? So it doesn't have to be, in any case, doesn't have to be restricted to reasoning. So comprehension of natural language, formal semantics, it might be much wider. And unfortunately, I think that this view and this sort of restriction very often comes from sort of traditional view of logic, where logic is only about reasoning, while reasoning is just a part of logic. Logic is also about structures, about computations, about processes. So now when you look around the world at the map of cognitive science institutes, you see that when they do modeling, they mostly use probabilistic approaches. And again, here very often there's a lot of tension between those few logicians that try to do cognition and people doing probabilistic modeling. So I don't want to enforce the tension. Quite opposite. I would like to say that these are really complementary approaches. And that actually logicians and people doing Bayesian modeling, probabilistic modeling, they could sort of collaborate. So for example, you can ask all the sort of questions, like given a Bayesian model, what is sort of a logical engine of that model? Or very often you look at the models, for example, learning models, and then you see that learning models, probabilistic statistic learning models, they need to start with some sort of space of possibilities. And then when you look into those papers, very often this is generated using logical methods or using some computational methods or methods coming straight from logic, so it somehow defines this space. And of course, logic can help. Logic can tell you, okay, how restrictive is your space? Can you define it wider? What properties have your space? So there's really a lot of opportunities for collaboration here that I think are not at that point really taken far enough. So what I would like to argue, I would like to convince you to this view that these expensive experiments, they are expensive, and messy computational models, they very often are in cognitive science, they should be built upon something more principled, something more foundational, and logic in particular is a good tool to do it. Again, logic understood broadly, understood in a way like a general tool to study information processing. There's another application of logical thinking in cognitive science, application that I think is very important and which is not very often picked up in psychology itself. mostly if you deal with cognitive theories and you deal with cognitive models, one thing is that you want to make experiments and compare your models to reality. But there's another aspect. Maybe you want to study, investigate your models, right? Maybe you have two models, and maybe it's very hard to distinguish them with respect to experimental data. But what you can do, you can study logical relationships between those models, right? So you can, for example, answer the question, are those models compatible? Maybe this is actually exactly the same model from some certain perspective if you are interested in something. There's more. You can study explanatory power of your model. So let's say I'm interested in models of language, in semantic models, and then I want to know, are my models powerful enough to capture some phenomena, to express some natural language constructions? And this is the question that logic traditionally studies, right? Maybe also your models express too much. Maybe your models express constructions that are really not in natural language, and then you can ask yourself a question, well, maybe I can have a weaker model. And finally, there's this point that I'm maybe particularly interested in. There's a computational plausibility of the model. So having a cognitive computational model, you need to ask, what is the computational complexity? Are the computations postulated by that model tractable? Are they even cognitively plausible? So you can easily imagine a model that actually implies, models some part of our cognition and implies that we are, for example, solving undecidable problems. That would be bad. Or maybe a bit better that we are solving intractable problems. But then if we are solving intractable problems, this is what the model says, then the question is, well, always, maybe under some conditions, maybe there are some parameters of the problem that make it tractable, and so on and so forth. So again, using that perspective, you can study those problems. So there is one more step, one more thing. So how you look at the different levels of explanation in cognitive science, and how logical perspective can help you to actually see that there are more levels that are traditionally assumed in cognitive science. And let me briefly talk about that right now. So let us think again about this turn in psychology in the 60s. So what is a cognitive task? So what is the reality of cognitive science these days? So you are running a lab and you are interested in something, and then you invite students, invite subjects, and they come into the lab. Let's say she sits at the chair, looks at the screen and solves some problem. Maybe language comprehension, maybe syllogistic reasoning, might be something with perception, might be something with vision. Right? So you isolate many things. You isolate a cognitive task, and you isolate your subject, you take it off the reality somehow. So you have this lab setting. And then how can you think about this task in the lab setting? Well, so you can think that your subject, she gets sort of an input, an initial state, an initial problem. And what you want her to do, you want her to transform that problem into some desired state. So you want her to say whether the syllogistic reasoning is correct. So you want her to transfer syllogistic reasoning into yes, no. You want her to identify the red dot on the screen. So, of course, you may set up different tasks in a different way. But basically, what you can think, and this is related to this input-output analogy, you can think that cognitive task is a function. It's a function that somehow goes from the possible set of initial states into the possible set of desired states. Right? So you sort of, it's a metaphor that turns out to be very useful, and that have turned out to be very useful in cognitive science. And then when you think about cognitive task in that way, when you think about cognitive task as information processing task, you may ask yourself, okay, as a psychologist, as a cognitive scientist, how can I explain that task? So what can I do to better understand understand that cognitive task. And famously, David Marr, who was a neuroscientist working on vision and who embraced that view a lot, he distinguished three possible levels of explanation in cognitive science. So there's a computational level. Right? So you may just want to specify this task, specify the function f, somehow, like, again, be precise. Right? So tell explicitly what are the problems, what is your problem that the cognitive ability of your subject is supposed to solve. And you already see how logic and philosophy can help here, mostly by making clear conceptual distinctions. It's already helpful here. But this is not where psychology, and for sure not where cognitive science ends, because there's another level of explanation, which is called algorithmic level. And if we solve the task, if we solve the task F, our cognitive task, then we do it somehow. Right? So what are the strategies we use? What are the heuristics we use? So this is the algorithmic level, to somehow to deduce, to understand the algorithms, the strategies that people use to solve a given task. Right? So in other words, you can say, how do we compute F? And now when you think about this, maybe something which is the most exciting about cognitive psychology. But there's a bad news. It's also the part that is very hard to get. Right? So, because we have no direct insight into humans' mind, so we cannot see what kind of strategy we are using, so there's no way. And for that, of course, people developed a lot of tricky experimental techniques, but always it's hard to interpret those data, and sometimes you get better insight, sometimes you get worse insight, but usually it's hard and it's complicated. Right? So this is really a place where a lot of work in psychology is done, and a lot of hard work and very tricky work, and you need to be really clever to come up with good design, come up with a relevant statistical analysis to get as close as you can to understanding what people actually do. And there's another level which is these days really blooming with cognitive neuroscience. It is implementation level. So you can ask, okay, how this is actually done in our neural activity? So what are the parts of our brain that light up in fMRI scanner? How they are connected? Right? And this is, of course, something many people are really excited about. But again, you need to take into account that a lot of data you get in neuroscience paper, they are strictly speaking correlations. So they say that given 5 cognitive tasks, in all of those tasks, this and that part of the brain was active, and then you still need to understand why those 5 tasks are connected. So it's not the neuroscience solves our problems, right? We still need to understand what's the underlying cognitive structure of the task. But of course, it can help. And I will also try to show you that even on this level, logic can contribute. I will just give a very brief example later. So now the idea is that even though logic can contribute on all those levels, this sort of modern logical perspective also can help you to extend this distinction, and you can think that there is more to explanation in cognitive science than just computational, algorithmic, and implementation. So the observation is that sort of logical analysis can inform you about intrinsic properties of the problem, about sort of structural properties of the problem, right? Properties that are sort of independent from particular algorithmic implementation. So you have a problem, and the problem has those properties that they restrict the class of possible algorithms that can solve that problem. For example, you may know that, well, if you want to solve that problem, you will need to use at least 152 bits of memory, right? Or you will need a lot of time, or you will need it won't be enough to use finite state machine, you will need to use somehow more powerful computational device. Or if you have 2 tasks, you may say, look, the first task is somehow intrinsically more complicated than the other task. So you can look into this, and if you think about it, it's sort of you are operating in between levels. So you still don't know what are the ways people solve the problem, but you know more than only specification of the problem. Using that perspective, you get sort of a restriction on the class of possible algorithms. Right? So I like to call it level 1.5, and this is this level where sort of logic may operate, may add something and actually predict behavior. So by restricting it also makes the work of psychologists easier, because suddenly they don't have to, they were considering the class of possible heuristics, and then we can tell them like, look, but people can do it, so you can cut off some of the heuristics because they couldn't work for that problem. And this is the property of the problem, not the property of your heuristics. So in a sense, there's nothing as practical as good theory, right? So if you have a good theory, then you can actually simplify your empirical work, simplify your experimental work, and also makes the interpretation easier and maybe pose new prediction, build new experiments. So this is something I would like to convince you to. Yeah. So I'm not claiming that this is. So of course, okay. That's also maybe it's important to say. So many people criticize this Marr distinction. They say that there's a lot of simplification in that also these days, right? But what I'm trying to say, what I'm trying to claim, that it actually helps to illustrate how the logic can play out in this cognitive science environment, right? So what I will try to do now, I will try to be very pragmatic. So I will try to give you examples. So give you examples where this story sort of works. And then by doing that, you will know what I mean by semantics, sort of information processing approach to logic. That's one thing. And the other thing, you will see what I really mean by this level 1.5. And then you will also see what are these experimental techniques and what are basically the possibilities for collaboration, maybe. And there will be a couple of examples. Okay. So first of all, of course, you can use logic to sort of formalize different tasks in cognitive science. So let me give this task, false belief task. So I mentioned this task because what Peter will talk later about will be somehow related. So the logic he will give, you may actually use to maybe explain, better understand the task. And even if you have no time to talk about that today, maybe it might be like a homework or like an exercise. So this is a task that is very much celebrated in social cognition. And there are many versions of this task, and this version is called Smarties task, but basically like it's the class of false belief tasks. So imagine the following situation. There's a kid, Peter, and Peter comes to your laboratory and you show him a tube of Smarties, right? So Smarties are these sweets in a tube, like M&Ms, right? And then you ask Peter, okay, so Peter doesn't know one thing. All those psychologists, they are really nasty people, so they just replace Smarties by pencils.
Can you explain it? I'm sorry. What is this Smarties?
Smarties is like a tube with sort of M&Ms inside, like sweets inside. But what happened to this tube that we...
It's as long as a pencil.
Yes, it's a long tube, yes. Sort of, it's a fancy thing. Yes, but unbeknownst to Peter, we just replaced Smarties by pencils. Right? And we ask Peter, what do you think is inside the Smarties tube? And of course, Peter will answer Smarties. That's what you would expect from Smarties tube. You would expect that Smarties are inside. And then we show to him that unfortunately, it's very disappointing, but there are no Smarties, they are just pencils. And then the crucial bit comes. So now we ask Peter, okay, but look, before we have shown you that there are pencils in the tube, what did you think was inside? Right? And then the question is what will be Peter's answer? And this is very puzzling and in cognitive science because that sort of depends on the age of Peter. So if Peter is younger than 4, then probably what Peter will answer, Peter will say that he actually thought that pencils are inside the tube. Right? When Peter is older than 4, then the chances increase that he will say, yeah, well, I thought that there will be Smarties, but to my disappointment, there are pencils in the tube. And there are many, well, so of course, interesting thing which is exciting for psychologists is this border, this threshold. So there is something about this age of 4 when we suddenly learn how to switch perspective. So look, this is sort of a temporal switching. So you need to switch, when you reason about the task, you need to switch your perspective back in time, right? But there are different versions of the task where Peter sits here and then there's Sally, and we somehow confuse Sally, and Sally is confused, and Sally has false beliefs, but Peter still might not be able, if he's a young kid, might not be able to understand that Sally can have false beliefs. And this is the reasoning, and this is the task, and of course what logic can do, this is one thing that logic can do, logic can sort of formalize the task. So they ask the question, what are the crucial parts of that reasoning? How different tasks of that form differ? In what respect they are similar? Because then maybe you can actually detect, on different tasks people behave a bit differently. So just by formalizing, maybe you can detect these crucial bits, psychologically crucial bits, and people try that. So Michiel van Lambergen, Keith Steining, they have a version of formalization in this very good book, Human Reasoning and Cognitive Science. It's, by the way, a great book that sort of overviews this project of using logic in cognitive science. But other people also tried. Torben Breuner used hybrid logic, and I think the style of hybrid logic, Seligman style, that Peter Blackburn will talk about later. So where you can actually account for this perspective switch. So you can think how to deal with that puzzle using hybrid logic. Also, Hans von Dithmarsch looked on formalization of that in dynamic epistemic logic, and in particular asked questions how different belief revisions policies interact with this sort of experiments, right? Experimental setup. So this sort of the formalization part, I won't give you any concrete formalization because then I would need to, of course, introduce some logic, and it would take too much time, but you can sort of, I hope you can imagine how to do that, right? So you can just have formulas that correspond to this natural language reasoning, and then you can see, okay, what are the deduction steps in your reasoning, and you can think, well, okay, there are differences, or this might be hard, or that might be why younger kids cannot do that, right? So this sort of formalization. So this is level 1, I would say. So you can use logic to do this computational level, sort of describe what's the problem, what's the reasoning problem underlying. Now, what I claim that we can go further, so that just by looking sort of logical properties of the problem, we can get to know something about behavior. So let me, for a starter, let me give you 2 very quick examples to also better illustrate the whole idea of 1.5. So think about syllogistic reasoning and think about proof theory. So as a logician, if you are interested in syllogistic reasoning, what you might be interested in building a formal system, building a logic, in which you can prove all the syllogisms. Right? So given 2 premises, you can prove the conclusion. Right? So you may want to have logic that proves all and only correct syllogistic reasonings. And for example, one of those logic proposed by Bart Hertz, but also building on the earlier work of Jan van Eyck, is using some sort of natural logic. So somehow that closely corresponds to linguistic form of your arguments. And then one thing you do in this approach, you track monotonicity. Right? So monotonicity somehow seems to be a very important property of reasoning, also of syllogistic reasoning. And one of those logics was proposed, and then when you look at that logic, so you take two premises, you make a proof of your conclusion, and then you say, okay, the proof is such and such, has such and such length. Right? And you make a proof for other solutions, oh, the proof is significantly longer. Right? So then you think, as a logician, you think like, look, I mean, it means that in this sense, from these two premises, it's somehow easier to draw this conclusion than that conclusion. Right? Somehow the length of the proof, the complexity of the proof somehow tells you how hard it is to draw this conclusion. But look, it's a completely arbitrary system. It was a system designed, nothing to do with cognitive science in a sense. But then when you look, and this is what you can get from the paper by Marr, if you now look at the length of these proofs in this arbitrary system and you compare them to the frequency with which people actually choose certain conclusions from certain premises, then you get a very good fit. You get amazingly good fit. So somehow this arbitrary proof system somehow tells you something about the increasing complexity of syllogistic reasoning. So it gives you good correlation, and in a sense it would also give you good predictions probably. Right? So this is what I call this level 1.5. So arbitrary logical system, but basically tells you something about the increasing property of syllogistic reasoning. And you use proof theory. So another example, you don't, okay, this is very classical thing, so again, psychology of reasoning. So I made this point, I don't want to talk only about psychology of reasoning, I want to go beyond psychology of reasoning. So let me give you a similar example where the same technique, the same sort of idea was used in a very different context. So this is a game, it's called Mastermind. I don't know, maybe you played Mastermind. So there are two players in that game. So there's a code maker. So codes consist of 4 pins of different colors, and there's a code breaker. And what code breaker does, code breaker tries to guess the code by proposing different hypotheses. And then he proposes hypotheses, and then code maker give some feedback. So it's like, look, so in your hypothesis, there are some pins in the wrong place, but they are of the right color, some pins are of the wrong color, and so on. So you get some quantificational information back. Based on this information, you sort of revise your hypothesis, right? And you propose a new one, and you get a new information. And then as you see, it's a finite board, so the game ends if you guess, then you win, and if you don't guess, then the code maker wins. And again, sort of a version of that game was implemented in a so-called Math Garden, which is a big educational project in the Netherlands, where using computerized environment, children learn mathematics and also logic, and this is part of logical task. And then one of the problems is that some items, some codes, are harder than others, right? So sometimes it's very hard to break the code, and somehow it's much easier. And now if you want to give this to kids, and if you want to convince their parents, so you need to tell them like, look, I will somehow assess the cognitive ability of your kid, and then I will give him a challenging puzzle, but not too hard, not too easy, right? We will make it fair. And this is what actually happens in the system. So we are trying to make it fair. But there was a problem with evaluating complexity of this task. And it turned out that one way to do it, you can sort of formalize that and build analytic tableau for mastermind games. And then you sort of, using this analytic tableau, you look at the proof, giving feedback, giving hypothesis, look at the proof whether this is a good code. And it turns out that somehow if you look at the structural complexity of this proof, it corresponds very nicely to the complexity the certain items pose for the kids in the system. And it also sort of codifies this information. The psychologists were very happy because it turned out that somehow like simply reasoning by cases is hard, right? But somehow, if you look, psychologically there are many factors, there are colors, a lot is going on here, right? But logic somehow takes off all these factors and only focus on the form. And it worked out, so you can actually do it. And this is another example where logic sort of predicts something without really going deep into psychology. So now you can say, well, but this is all a bit arbitrary, right? So I gave you those logics, and they're like arbitrary systems. So indeed they predict something. I mean, this is the whole point, that they are arbitrary, right? But indeed, in these two cases, they were like real logics, like, you know, formulas, and maybe you could formalize it differently, right? And probably you could, and maybe you could formalize it differently and get the same results. I mean, that's the whole point of the game. So here, as I was also supposed to talk something about my research, let me give you an example of doing that using more semantic perspective, where we don't have an explicit logic, but still we look into the structural properties of the problem. Yes, so we want to somehow capture these properties, and so they are sort of independent from particular formalizations. So on that you could build, maybe you could implement different logical systems, but hopefully the results will stay the same no matter what is your logical implementation. So this is the class of problems we recently looked at. So we look at so-called turn-based games, and they come in different flavors. And they are this is a very popular experimental paradigm in psychology. Of course, interacts with game theory, where you want to see how deep people can reason about other people. Right? So this is called the matrix game that was extensively studied. Let me explain you the idea. Let's focus first on that game. Right? So you have two players. You have player 1 that sort of acts vertically, and you have player 2 that acts horizontally. So you have a token in square A, and then player 1 can either stay in A or can move the token to B. If and only if he moves the token to B, then player 2 gets to decide. So player 2 can either stay or can go to the right. If the token is in square C, then again player 1 can choose and can either stay or go up. Okay, so these numbers, they are payoffs, right? So if the token ends up in the square A, meaning that player 1 decides to stay, then player 1 gets 3 and player 2 gets 4. And the same for B, C, and D. And now you ask people to play that game, and of course those payoffs, they somehow correspond to some real payoffs, like, I don't know, dollars or course credits or whatever. Well, and people somehow solve those games, and they somehow reason about the games, and one strategy to reason about the games is backward induction. So this is what game theory would sort of prescribe as a good strategy. So how can you think about that? Well, you can start from the end. You can think, okay, if let's imagine that I'm player 1. If I had to choose whether to stay in C or go to D, well, I would go to D because I prefer 2 than 1. But then player 2, he knows it. So he knows that if I'm in C, I will go to D. So then if he is to decide in B, he actually prefers 2 over 1. So he prefers to stay than go to C, because he knows that if he goes to C, then I will move to D. Right? So I know that if the game is in stage B, it will stay in stage B. So now I think, well, I prefer 4 over 3, so I go to B. And this sort of a backward induction. Now when you think, it involves, I have to think what my opponent believes about what I know, sort of right? So this is the higher order reasoning, and this is very crucial in real life. So when you face any negotiations or when you play games, then we do it all the time. We're pretty good at it. Some of us are better, like chess masters are crucially better than other people, but basically we cannot do much more than 3 stages. So we can think like, I can think what Olivier thinks, what I believe, but maybe I cannot anymore think what Olivier thinks that you go into this loop, right? But people deal with those problems, and those problems, they were created to somehow test this sort of abilities. And this is a version of the problem that game theoretically it's sort of equivalent version. So it's called marble drop game. So again, I just briefly explained the idea. So now it's a different representation. So here you have zero order game. So you have a marble, white marble, and you can either open left or right gate. And if you open, the marble will either fall into the right or to the left bin. And if you are the blue player controlling blue gate, you want white marble to end up in the bin with the darkest blue marble. And probably you cannot see very clearly the colors. Doesn't matter. This is that thing. The idea is clear. So you would open this. So this is the zero sort of depth reasoning, right? You just think, okay, the marble go here. So this is the game where you have to do first order reasoning. So you actually have to think about your opponents. So your opponent wants white marble end up in the bin with the darkest yellow color. So now you think, okay, if the game goes here, what is she going to do? Well, she's going to go here, right? Because this is darker than that. But then, as I prefer that marble than that marble, I go left. This is first order. So then you go to second order. So sort of becomes more tricky, because then you have to think what she will think here about what you are going to do here, right? That's really the second order reasoning. And now, this is the reasoning I explained here, right? So now you can think not about, so somehow these are marbles, they correspond to payoffs. And you can make the reasoning. And in a sense, if you think about those two games, so if you set up payoffs in an analogical way, then you will get, like game theoretically, you will get things that are equivalent. Right? So from the structural perspective, from this logical perspective, you may find items of this game giving the right payoff distribution, items of this game that are sort of equivalent. So the first thing to say is that there are differences in subject behavior on those two games, even if they are equivalent. So that already tells you that there are things that logic maybe cannot explain. But there are some systematic differences between those two games. And this is what we are interested in. We are interested in the systematic differences. So for example, we are interested to know whether A is harder or D is harder, and how it depends on some properties of the game. I want to know it before I run the experiment. I want to know it before I use it as a training tool for negotiators. Right? So now I will focus on that game and look into some structural properties of that game. Well, so this is that game, right? This is called a decision tree. This is how you would represent that game in, say, game theory. It's an extensive form game, how you would call it in game theory. So what's the representation? Well, you have three nodes, somehow corresponds to the gates. And in the first node, first player can either go left, and then he gets certain payoffs, or can go right. If he goes right, then the second player can decide, and again, left or right. And then the third node is again controlled by the first player that can again choose left or right. Right? And you can use backward induction. So backward induction, you somehow work from the bottom of the tree to the up to get what's the optimal rational strategy, and that will give you this optimal rational strategies like Nash equilibrium, in this case subgame perfect Nash equilibrium. And this is what backward induction gives you. So the question is, okay, are people using backward induction? And if not, why? And moreover, just looking on the shape of the tree, can you guess why some items are harder than the other items? So let me for a moment assume that the game is generic. It means that for each player, distinct end nodes have different payoffs. So look, this is the assumption that corresponds with my pictures, because simply I was using different shades of blue and different shades of yellow. So I don't bring anything new here. And what I want to know what are cognitively important structural properties of those trees. So if you're a logician, especially if you are a logician that deals with computations, and when you look at the tree, then you think about all these hierarchies, like Klini-Mostowski arithmetic hierarchy, I don't know, polynomial time hierarchies, all those hierarchies where things alternate. Right? So here you can think that in those trees, players alternate, the move alternates, and you can sort of categorize those trees with respect to somehow the depth. If you think about modal logic, you think about the modal depth of the formula, for example, right? So if you assume that the players strictly alternate in that game, okay, assume because these are the games we picked, then you say that in lambda E1 tree, all the nodes are controlled by player I, and then this is an inductive definition. In a lambda ik tree, there are k alternations starting with the it player. Right? So for example, if you have a game like this is lambda 1 tree. Well, it starts with a move by player 1, and there are 3 alternations. So then the crucial bit we are looking right now is the alternations of the players. And why? I mean, maybe just a very brief intuition. Like, think about the situation where I control all the gates, I control all the nodes. Of course, it's trivial, right? I can just go wherever I want. It's also very easy for people. So somehow, look, if you look at this alternation, it starts to correspond to the depth of higher order reasoning, right? So that seems to capture that. So now you have 2 trees, there are 2 lambda 1 trees, and I think they violate one of the assumptions I just realized, because there's no strict alternation. Whatever. So according to this very simple perspective, they're at the same sort of level of the hierarchy. But then, if you play left game or if you play right game, of course, one of them is much easier. Right? The left game is trivial, because as a first player, you will just go and get 999. So you won't even go into this reasoning. I mean, if you would start with backward induction, you wouldn't sort of notice, you would overlook that on purpose, and you would just go through the whole reasoning, but you don't have to. It's simple. So if you really want to use that, you need to somehow take into account the interaction of this alternation hierarchy with the payer distribution. So one idea is here that there's another strategy except backward induction which you could use, which is sort of forward reasoning, call it forward reasoning with backtracking. So I look for the highest payoff, and then I reason if I can get there. If I can get there, fine. If I cannot get there, I backtrack. So for example, I pick the second best reasoning, and I try to get there. This is sort of another alternative, another possible strategy. And then, if people would apply that strategy, then it would, among others, mean that if you cut those trees, so restrict those trees to the highest payoff for the first player, so you will get something which I call T minus. So in one case you get lambda 1 1 tree, in the other case you get lambda 1 tree. So in a sense, just focusing on the highest payoff will reduce the levels in one case, but will keep the levels sort of constant in the other case. So now the sort of simple idea is that the complexity of such game corresponds to the depth of this T minus tree, right? This is sort of a simple idea that is only based on the structural properties of this abstract representation, right? So the sort of the conjecture is that if you experimental conjecture that if you take two marble drop game trials T1 and T2, then T1 is easier for participants than T2 if and only if T1 minus is lower in the tree alternation hierarchy than T minus 2. Simplifies a lot. So okay, so we wanted to know that. So now I talked about this collaboration. So you're going to the lab and you can actually collaborate with psychologists. So this is the game we showed to our participants. So this is the marble drop game. And there are marbles, maybe now colors are better visible. gates. This is the time counter, which you won't be able to see. Doesn't matter, but I hope you can see this green dot here. Sort of, right? So what we are doing, we're really all about that green dot. So what this green dot does, it tracks your eye movements. It's like eye tracking experiment. So now when you look, I don't know if you can see it, but okay, people were solving that game. So we were asked the first players, okay, are you going left or are you going right? And then we want to see, somehow has an insight into the reasoning strategies, so it's somehow where he looks. Now you see this dot, I don't know if you can see it, but it's jumping all over the place. Well, so now imagine that we gather this, there are like hundreds of thousands of these data points, and you want to somehow know what's the strategy. So already you see it's hard. You have to do some cluster analysis, you have to interpret something. But also the feeling is that here we didn't really see backward induction, right? The guy was looking at the gates, sort of irrelevant because the structure is fixed. So if you would see backward induction, you would just see that, like, you first compare those two, then you compare the one with the highest payoff with that, and then you sort of keep backtracking. And actually, you could really see it. And some people really did it. And especially when you train people with this sort of experiments, they get it. At some point, there's a very interesting point I'm not really going to talk about. It's somehow like the learning aspect of all those experiments. But here, if you look, the green dot starts here, and then you will see something that really resembles, sort of resembles backtracking, resembles backward induction. Of course, still the question is, are people really on average using backward induction or not? And note that, I don't know why we have this. So now that our prediction, like looking at the structural properties of the tree, our prediction was that actually not, that they use this sort of forward reasoning with backtracking. And this is what you can get. I won't go into details here, but actually if you look into the results, so then you get that the prediction is satisfied, that actually the people take less time and are more accurate on the game items that are somehow lower in this hierarchy when you cut them to the highest payoff. So it seems that you can predict that only based on the structural properties, and they seem to be responsible for the cognitive difficulty. Those results, they should sort of generalize to other 10-based games. So there might be a different base condition, but somehow the relation between items should obey that. And the question why, the answer is that this forward reasoning with backtracking sort of avoids this higher order reasoning. So when you think about it, that we also simulate, I'm not going to talk about it, it actually makes sense, it's more efficient. Computationally, for our trees, it's in a sense better. So this really makes sense. Okay, so this is one example where you sort of looked into the semantic of the task. So let me briefly give you another example that is sort of more from my past, but it's about natural language semantics. And I have some time, or I can be quick if you want. I mean, basically here the idea is that we look at sort of a very natural candidate for estimating these things is just looking straight into computability. Right? Sort of just look what are the minimal devices, minimal computation that can solve the task. So you sort of look at computational resource constraints, you ask questions about time and memory, and you sort of think about your agents as bounded agents, right? So they have only certain amount of resources available. And again, sort of these computational properties, they somehow lie on this level, because these are not properties of concrete implementations, they're properties of your problems. So I can tell it without looking into algorithms, actually. So here we really focus on sentences, right? So we focus on sentences with quantifiers like all poets have low self-esteem, some didn't dance Newton on the table, at least an even number, most less than half many of you, right? And not reasoning, but verification. So can you verify whether the sentence is true or false given a model? And it happens that logicians, they've been obsessed with that problem in a sense, right? Because this is the core of formal semantics. So you have given a model, you have given a universe, you have given two predicates, and those quantifiers, they talk about the relation between A and B. So some means that the intersection is non-empty, right? All means that A is a subset of B. And there's the whole theory of generalized quantifiers that actually studies that problem. And there are hundreds of very fine-grained logical distinctions between those different quantifiers. So one question is, what about definability of those different quantifiers? Some are definable in first-order logic, some are not, some are definable in weaker fragments, and it already gives you some estimation. But one thing which you can do, you can also look at the corresponding computation, right? So this is the idea going back to the 80s, where with every quantifier you can associate minimal computational device that will, given the model, check whether the quantifier sentence is true. And that association somehow depends on the definability property of those quantifiers. So very quickly, if you think about Aristotelian quantifiers, for example, like all sum, each of them corresponds to finite state automata with only two states. Right? So for all, if you want to know all A's are B, you are looking for a counterexample A that is not B, and then you go to rejecting state, and then you stay in rejecting state. Otherwise, you somehow stay in accepting state. So this sort of captures this idea of looking for, in this case, for counterexamples, right? If you think about it's all. If you think about sum, then you sort of reverse the states, and then you think about positive examples. So this is very simple. Computational is extremely simple. But then again, it's sort of a hierarchy, so it's all based on these differences. So if you think about cardinal quantifiers, so guys like more than 2, less than 7, between 8 and 11, then you need to count, right? And somehow, if you look at the corresponding automata, this is what you get, that the number of states will depend on the number mentioned in the quantifier. So if you want to count, if you want to check if it's true that more than 2 A's are B, well, you look for 2 A's that are B, so you are here. It's not enough because it's more than 2, so you find another one, you stay in accepting state, you find. Yeah, so you just count it. So of course, you imagine those automata, they will grow in size when the numbers grow. Those quantifiers are very interesting from computational point of view, like an even number of and an odd number of. Right? So those guys are sort of tricky because they are non-monotone, basically. So how you can deal with them? So is it true that, what do I have, an even number of A's are B? Well, if there are no A's that are B, 0 is an even number. So I start with an accepting state. If I find one example, I move to a rejecting state. If I find another one, 2 is even number, 3 is odd, 4 is even. So you loop. So this is a minimal model, but you have a loop. You didn't have this loop, you didn't have the cycle in the other models. So it already you feel it sort of adds some complexity. And another way of complexity, this is first order definable, this is first order definable, this is not first order definable. Still finite automata, not first order definable. You can sort of go even higher, you think about most. More than half, less than half. This quantifier is also not first order definable, and it actually cannot be computed by finite automata. So now think why. If I have a sentence more than half A's are B, and I want to have a computational procedure that solves my problem for every size of the universe, I don't know how many A's and B's I will get. So I have to have something universal. So I have to be able to somehow count the number of A's and B's and compare it. And to do that, you can use, for example, push-down automata. So you have to have some sort of a working memory, like a stack in this case. Something is unbounded. So the number of states is always bounded, but here you need something unbounded. So you see that computationally speaking, this is significantly harder. So the other ones correspond to regular languages if you are in a computational linguistics, mathematical linguistics. This corresponds to context-free languages, right, in Chomsky hierarchy. So this is really harder. So this is the model that goes back to the 80s, was actually proposed in the 80s by Johann van Bentem. And then it seems like for 20 years, no one was really interested in asking the question, is this model really cognitively plausible? So do those distinctions have anything to do with how we understand quantifiers, how we verify quantifiers? And this was a little task we tried. So we ran a number of simple experiments where basically you get a picture like this, or similar, and you are asked to say, is it the case that all the cars are yellow? Easy, probably already got it. Is it the case that more than 7 cars are black? Guess you know it already. Is it the case that more than half of the cars are black? Maybe you already feel that, that there might be some differences. So what's important about this experimental design, that we did it in a way where more than 7 and fewer than 8 were equivalent to more than half and less than half. So, because we always had 15 objects. But still what you will see, there are crucial differences in the people behavior and in the amount of cognitive resources that got engaged. And those are the differences that sometimes are consistent with the model. So first thing we did, we just asked people to do it and we checked reaction times. So how much time do we need to actually make a decision? And it turns out, as you would predict, that this is very easy. This is sort of a perceptual thing. You see examples, counterexamples. This numerical and parity, well, this numerical, they actually grow. The bigger the number, it will grow. Parity somehow also takes some time, but proportional quantifiers are really the hardest. So they take a lot of time, and there are no differences in accuracy. So people are very good at this. People solve their tasks perfectly. So that's why I'm only showing you reaction times. Then I promised to say something about logic and neuroscience. So actually, the idea was, but is this distinction of first order and higher order quantifiers actually neurally plausible? And people in UPenn in Philadelphia, they put subjects in the fMRI scanner. So you are lying there and you see the picture and you are saying, okay, most of the dots are blue. You are pressing the buttons. It takes 2 or 3 years to design those experiments. And then what you get that yes, there are differences. So it turns out that all quantifiers were associated with the part of the brain which we believe is responsible for numerosity, which somehow proves that quantification embeds number sense in language. But only higher order quantifiers, like more than half and less than half, only those quantifiers engage working memory. So they are, even on this level, they are harder, and they engage exactly the part that you would sort of predict from your model. And this is the experiment that was completely motivated by this logical predictions. Actually, it happened sort of by accident. So Robin Clark was giving a talk on semantic automata. Corey Macmillan was supposed to give a next talk to students about neuroscience. I said, like, look, Robin, but we could run experiments about that, right? So it's really this sort of a collaboration that just happened because it gives nice predictions. Still, you might be always skeptic about neuroscientific research, so we tried other stuff. So is it really that those proportional quantifiers are significantly harder? So one idea to compare that is also what people do in psychology very often, is to compare healthy subjects with patients. So in this case, we chose patients with schizophrenia, and in particular, we chose a cohort of patients that were known to have problems with working memory. And exactly their problems with working memory, actually, that was also checked, they were corresponding to this part of the brain. So I wanted to compare those two groups on quantifier tasks. And this is what we did. So orange are patients, green are our control subjects, healthy subjects, and this is the reaction time. So what you see that patients, they basically take longer. And this is a well-known thing in the schizophrenia literature. There's the slowdown effect. So they are somehow slower. Nothing surprising here. But now, when you look at the accuracy data, you see that the patients are as good as control subjects on Aristotelian quantifiers, on numerical quantifiers, and even on parity quantifiers. And the only crucial difference is this proportional quantifier. So this is indeed, even they had a lot of time, there was no time restriction, they were sort of unable to deal with patients, unable to deal with proportional quantifiers as accurately as healthy subjects. This again another example how these computational insights let you predict something. And actually you can even push the story a bit further. You can look into distributions. That's what we did recently actually this year. We looked into distribution of different quantifiers in natural language. So we look into different corpora and you would guess, well, maybe it's actually the case that those quantifiers that are harder, computationally harder, they are less frequent. And maybe there are some power laws that actually governs that. And it turns out, yes, it's the case, that if you look at corpora, of course, this is a very preliminary result. We looked at a couple of corpora, but it seems that there's something like this going on, that again, these increasing properties of quantifiers somehow also might be partially at least responsible for the distribution in natural language, which I find like a quite interesting result, especially the other results that draw a link between complexity and distribution in natural language. Yes, so this was another story where you can actually use computations to get experiments going and to predict things, even though, of course, we don't know what are the strategies people use to verify those quantifiers. We have no clue because these eye-tracking experiments, in the case of quantifiers, they bring extremely messy data. We were unable to resolve what's going on there. So people tried, we tried, very hard to interpret. But having those sort of theory, we already get something. So let me give you a very short conclusion. So what I would argue for and what I would like to advocate for is that like this computational awareness in semantics, this was my second example, but also in logic of agency, this was my first example, it can help to bridge these disciplines to cognitive science. So it can help to design experiments, it can help to enrich our knowledge about cognition. And that can, as you saw from the example, that can go radically beyond psychology of reasoning. So those logics, those approaches, they can actually focus on processing rather than on logical correctness, right? So suddenly we are not only interested in how many people said yes, how many people said no. We are sort of interested in working memory engagement, in reaction time, maybe in parallel processing. We are interested in processing because those logic are about processing. So also, it forces us to use sort of more sophisticated experimental designs, right? Because we're suddenly not only about pen and paper experiments where we look at the error rate, but we are also interested in measuring eye tracking, like trying to get to know how people process information. And that, of course, calls for collaboration, right? More than ever. So if you really want to use this modern logic, if you really want to have insight into processing, then you really need to collaborate with people, right? And this seems to be very important. So what I was trying to basically convince you is that this modern logic is a part of cognitive science toolbox and can be fruitfully used. And it sort of revolves around interpretation, information, computation. So it revolves around processes, so it can go beyond the experiment, beyond the results. It can go into the processes, into the sort of cognitive processes. It helps predict behavior, right? And in this sense, it sort of can help to extend our perspective, our resolution on experimental design and on cognition. So this is what I called at the beginning 1.5. And yes, so of course there are many more examples like Wason selection tasks, and I didn't have time to cover all of this, also didn't have time to really cover all the details here. So just a couple of things. So if you would like to see more, there's this paper we just finished with Alistair Isaac and Rineke Verbluche, which gives sort of a survey paper overview of what's going on, the interaction of cognitive science and logic. And also we have a special issue running in Journal of Logic, Language and Information with Rineke, and we just sent the first paper to production. So more examples are coming soon. And there's also a website of various courses with slides and bibliography that you can easily Google. So thank you.